Thanks for coming. It's great to see so many people here for a talk about a networking protocol. I'm Ryland Degnan, CTO of Netify. Prior to that, I was on the Edge platform team at Netflix that created RSocket, so I'm really thrilled to talk today about what RSocket is and, more importantly, sort of the place that it fits into your cloud application and what you can build with it. So there's been other really good talks about the nuts and bolts of RSocket, sort of how the protocol spec works and why it's designed the way it is. I'm more interested in going into sort of code and explaining how to build things with it. If you're interested in the protocol itself, I would point you to a really good talk just earlier this month from Ben Hale of Pivotal, who really went into sort of the design decisions, and you can find that on YouTube. So communication in the cloud is a challenge. Enterprises are in this transition phase, moving from this relatively constrained environment of the data center into this wild west of the cloud, where there's a whole new set of problems. And there's growing realization that old approaches to networking don't really translate to this new world. So these are some quotes from a recent CNCF conference. The network is the unsolved problem of the cloud. We need the network to be a first-class citizen. A standard approach to connecting and communicating with microservices is needed. So there's growing consensus that this is a big problem, and the way to solve this problem is through some sort of standardization. Unfortunately, a typical cloud strategy looks something like this. This is a real thing. They tried to do this in World War II. I think it flew for one flight, and then they scrapped the idea. But unfortunately, instead of spending our effort coming up with new standards and protocols to meet the new challenges of the cloud, too often the approach taken is sort of bolt on something, take some legacy code that kind of works and get it in the cloud at all costs. Slap a sidecar on it, whatever, just get it out there. And that's approach works up to a certain extent, but as these guys discovered, it's not exactly the best you can do. And when things go wrong, the price of failure is incredible. So, for example, Snapchat would be profitable if it weren't for their cloud spend. And these kind of problems happen more often than you think. On the Netflix Edge platform team, we're constantly striving to lower cloud costs. Unless you're very careful about it, things can go wrong really quickly. So RSocket is designed to simplify the problem of cloud communication by essentially taking this same set of problems that all applications in the cloud have and solving them not in sort of one library in one platform, but at a protocol level, so you can have interoperability between the different parts of your system. So every cloud application has essentially the same small set of concerns, right? Flow control, service discovery, load balancing. What do you do when a session is broken and you have to resume the state of the session? What about security? How does that work when you're using different transports, WebSocket or TCP, AIR-on, and then things like observability, gathering metrics and insights about your application, tracing, changing the behavior of your application in certain ways via fault injection or distributed properties. These things are pretty common and really necessary to operate a reliable service in the cloud. And so what RSocket gives you is this language on top of which you can implement these things. And a lot of them are built into the protocol itself. So Reactive Socket uses reactive stream style flow control, which already has excellent support in a number of different languages. And so sort of invisibly to the application developer, you just get for free the ability to have traffic shift around based on availability. You don't have to configure circuit breakers anymore. So RSocket has a number of contributors. A lot of them were sort of leading movers to the cloud, Netflix among them, but also Facebook, Pivotal, and Alibaba. And so it's really built out of experience in terms of encountering these problems, seeing what can go wrong, and then trying to go back and really design a proper solution and not the bolted-on wings to the tank approach. So modern cloud applications are complex, right? This is a really complicated problem. and it's complicated in ways that we've never seen before. So applications today, more than ever, are distributed, heterogeneous, and interactive. It's a common mistake to think about your application just purely in terms of the backend infrastructure. Right? Today, like, everybody's walking around with a computer in their pocket that exceeds the capacity of the servers of just a few years ago. So applications are distributed not just globally, not just geographically, but also in terms of where the compute is run on the stack. So we have things like edge compute and fog computing, and then increasingly running compute on your users' devices. And so this distinction between client and server is disappearing. People don't write applications now as this monolithic server and a thin client. And that presents a whole set of problems. And not just that, so these multiple axes of complexity going on. One of them is sort of the deployment topology, where your application is deployed both geographically and sort of where the compute runs in your data center or the cloud. Another one is new platforms and frameworks. So if you're distributing your application to a mobile phone, then you have to deal with the mobile phone platform. Similarly with web browsers, running your application in the cloud is a platform. And then in addition to that, there's these different protocols or interaction models that we increasingly come to expect. People are not satisfied to click refresh again and again on a web page waiting for an answer to their query. They want it to be delivered to them in real time. So there's more and more interest in streaming interaction models, peer-to-peer interactions, all of which become part of this complexity. And so to dig into a little bit more detail in these, so the deployment topologies. There's multiple public cloud providers which are increasingly being used together, not just one at a time. In addition to that, there's functionality still in the data center or private cloud, many of which has good reasons to be there and should never move. And on top of that, there's sort of the deployment to your users' devices. And then beyond that, on top of the deployment topology, you have these platforms and frameworks. So you have these multiple orchestration platforms, things like Nomad or Kubernetes, Mesosphere, and then things like Lambda, function as a service, that are becoming an important part of your application now. And then you have sort of developer frameworks like Tomcat or Node or Akka. And you want the ability to use all these things, and you want them to work together, but you don't want to have to constantly be reinventing the wheel every time you want to add a new framework or orchestration platform. And you don't want to lock yourself into just one of those and solve all your problems in this sort of walled garden, because immediately when you go outside that walled garden, you have to, again, solve all the same problems. And then so the interaction model. So there's still, most traffic on the internet is probably still request response. So typically that might run over HTTP, it might be a database query. That's one interaction model, call it request reply. Another one of increasing importance is the streaming interaction model. So both ingesting data that your users are generating and doing real-time stream processing, moving data from place to place. And then there's a sort of RPC style interaction model, which has a different set of concerns. And you might be more interested in extremely low latency. So you might be interested in network protocols, RDMA or InfiniBand in the data center. And then beyond that, there's this sort of real-time and peer-to-peer interaction model. So you might want your users to be able to communicate with each other, a web browser to a mobile phone, or streaming video to a set-top box. And so all of these are sort of a viable part of your application. But how do we approach this problem of making sense of this sort of mess of incoherent and incompatible protocols and services, right? On the face of it, it seems like a pretty daunting problem. And indeed, with current technology, you're essentially stuck with reinventing the wheel every time you want one of these new interaction models. Because every one of these protocols handles things like security, resumability, flow control, completely different. And on different languages, it's going to be different. So you end up with these weird incompatibilities and a lot of glue code that you have to write to when all you really wanted to do is you had a business case for like streaming, and then suddenly you're deep in the weeds with Kafka and Akka and things that you didn't necessarily want to have to set up and maintain on a daily basis. And so the approach RSocket takes is there are things that we can't really do anything about. One of these is deployment topology. It's very tempting to say, like Snapchat, for example, I'm just going to run all my code on Google App Engine. It's all going to be Python. Everything's going to be great. Everybody's going to use the same set of common libraries, and we'll be fine. Well, that works up until you're sort of locked into a $500 million a year cloud deal, and you can't move off of that platform because you've locked yourself in. In addition, that doesn't really address any of the difficulties of building a distributed system. You're just locking yourself into one topology. The other is this proliferation of development frameworks. So it's a mistake, I think, to say, to choose a particular framework and force everybody to adopt that framework. Inevitably, there are reasons that people want to, say, use Node as a backend for a web service or Java for a server-side application. Each of these development frameworks has a good place, and it's important to allow developers the freedom to choose what the best tool for the job is. But the third thing is something we can do something about, because although there are several interaction models, it's still sort of a small, finite set, and that's something we can actually standardize on and form a protocol around. So we don't have to keep reinventing the wheel again and again. And that's exactly what RSocket tries to do. So broadly speaking, like the RSocket contract, this is in Java, but it looks very much the same in other languages, takes these interaction models and sort of gives the developer an interface that represents them. And this happens to be using the reactive streams implementation, which is the flux and mono types. But what it returns and what it accepts are just publishers, reactive streams publishers. And so this then gets translated on the network to binary frames that represent these interactions. So every time I request an item from a publisher, that gets translated into a request end frame, which gets sent to the receiver, and it gets translated into the appropriate method call on the other side. And so this lets us solve these cross-cutting problems like flow control across many different languages, completely abstracted from where your code is deployed or what it's running on. So a good example is flow control. This is not mine. This is a TCP versus UDP example, but the same applies to sort of RSocket versus HTTP. HTTP is a little like pouring water on your face. If you can't swallow fast enough, then it's going to go everywhere. Versus RSocket is more like drinking out of a bottle. It's got flow control end to end, so you don't have to worry about circuit breakers and configuring flow throughout your entire application. And in a distributed system, this is really difficult. I don't know of any other network protocol for which flow control can propagate more than one network hop. So from a browser, you can hit an intermediate web service that talks to a database and streams out only the items that it needs from the database. That's a really hard problem. And that can happen whether the intermediate transports are TCP or HTTP, WebSocket or Aeron. It happens above at the transport layer, at the application layer, which is where you have access to this information. And importantly, it's reactive stream style flow control. So you're requesting a number of logical items, not some number of bytes. Sort of like gRPC, for example, has byte level flow control because they delegate it to HTTP2. But that's not always very ergonomic for a developer, right? If I ask you how many hamburgers you would like to have, it's a little odd if you say 1.5 milliliter or something. It's a valid response, but it's not something that I can translate into the things that I know about. So how does this look in practice? So it's actually really easy to set up an RSocket, and you can see it's completely abstracted from the actual transport that you plug into it. So in Java, this is an example in Java. There's a factory, and you can plug in your transport. So this just happens to be establishing a RSocket connection to a TCP RSocket server at this address. And then what does that give you? It gives you this interface that I talked about before, and then you can start to call the different interaction models on it. So for example, request response. And this is a little bit hard to use because it accepts sort of an arbitrary payload. RSocket's not opinionated about what the data types that you pass over it are. So it accepts a binary payload that has both metadata and data associated with it. So that's cool, but it's a little too low level for most use cases. So sort of what I wanted to talk about more today and demo is this RSocketRPC, which essentially does something similar to gRPC. Lets you start with an IDL that expresses your the service that you want to offer, and then allows you to generate clients and servers in any language you like, and then plug in the transport that you'd like. So for example, if I were to find a record service that talks to a database, essentially, then in Java, it would generate the record service client for me. I could plug in whatever RSocket I like there, and that's going to handle all of the serialization and deserialization for those items that I'm passing over. So before I go into demo, there's a couple of sort of Netlify contributions to the RSocket open source project. One of these is the RSocketRPC library. The two existing libraries are RSocketRPC Java and RSocketRPC JavaScript, and sort of expected to come soon, probably by the end of the year. We're looking at Kotlin, .NET, and C++. So there's a growing set of languages supported. And the other thing I'd like to demo is the RSocket Akka transport. So the default transport for RSocket uses Netty, but as I said, it's completely non-opinionated about how the bytes get transported. And so I'll show you how simple it is to plug in Akka as a transport. And that's also available as an open source plugin to RSocket. And that in itself is really cool because as opposed to sort of Akka gRPC, for example, shades all of Netty, and then you have to deal with context switching between the Netty event loop and your Akka actor system, whereas this is actually Akka top to bottom. Okay, so let's go into some demo code. Can everybody see this? Okay, so this is just the protobuf file that I was talking about before. So I just wanted to show a quick example of how to use RSocketRPC to make several services that talk to each other and what you can actually do with it. Okay, so in this demo, there's a database. There's a Postgres database. We're going to define a record service that talks to the database. And the database is full of superheroes, full of sort of Marvel characters that have a bunch of statistics associated with them. So they have sort of their name and alias, superpowers, secret identities. So it's just some data to play with, really. And then on top of that, we'll say, what can we do with these characters? So we'll define a ranking service that takes a couple characters and returns the one that is better. And then the tournament service that is able to stream through the database, pit the characters one by one against each other, and then stream the results until you finally arrive at a winner. So 3 services that call one another. So here's an example of the record service. And by the way, if there's any questions, don't hesitate to stop me and ask questions. I'll just go through this, and then I'll try to leave some time at the end. So this is using Slick to talk to the Postgres database, and then stream out the records. And as you can see, this is very similar to the Java example I showed before, except instead of the Java RSocket TCP server transport, this is plugging in the Akka TCP server transport. And I think it's sort of a testament to the way RSocket is designed, that this is literally all you have to do to plug in Akka. What RSocket requires of its transport is just simply take whatever that transport is and turn it into a publisher of bytes, essentially. So Akka has some great utilities to deal with the framing, and then it just returns the TCP duplex connection back to the RSocket framework. And then from then on, RSocket takes care of all of the RSocket-specific frame encoding and decoding. So this is like 30 lines of code versus 500,000 lines of code for gRPC. Okay, so if I were to run this thing, okay, so I've bound to localhost on port 7001. So how do I talk to that? Again, this looks very similar. I'm going to plug in the Akka TCP client transport, point it to where I'm running my server, and then take the generated code. So this is generated code, so it's not going to look super pretty. But this is essentially the code that does the encoding and decoding of the types that I specified and maps my types onto the RSocket interaction models. So in this case, it's a request stream. So you can see it's defining my records method, takes care of the serialization of the data and then metadata that I pass in, and then calls RSocket request stream and maps the deserializer. So again, it's all it's adding on top of RSocket is this sort of ergonomic model where I can define services and then map it onto the RSocket interactions. Okay, so what is this going to do? So this is just going to define a records request, call my service over the network, and then print out the results. And there we go. So this is just, I asked for 40 items, so I got 40 items from the database. Each of them have sort of a picture that is associated with whatever that character is. But that's all I've done. That's all the code. Okay, so what's sort of the next thing to do? Now I've got sort of a point-to-point connection going on. But what about all the other stuff? What about load balancing, service discovery, metrics, all that other stuff? Well, the cool thing about RSocket, as I was saying, is you can hide all that behind the RSocket interface. So I can keep my code exactly the same and change the way that I construct the RSocket now, and then suddenly, magically, I get all this functionality. And to do that, what we've built at Netify is an RSocket router. So it takes RSocket frames and allows anybody to connect into this network of brokers and automatically handles load balancing at the network layer. So as an application developer, suddenly I don't need to worry about Eureka. I don't need to contact some external service registry. I don't need to worry about health checks. I don't need to worry about circuit breakers. I can just talk to services, logical services within the network, and the routing happens automatically. So how does this work? Proteus, which is the RSocket broker, forms a network among itself, sort of a gossip network, and it knows exactly what's connected to each node in this network. So then I can connect in from a web browser or phone or a backend service. And when I connect in, I advertise to the broker what services I support, and that handles service discovery. So as soon as I connect in, other people, it will start to route traffic for that service to me immediately, back over the same RSocket connection. Because again, RSocket is totally bidirectional, and there's no distinction between server and client. So in this world, the browser might offer services to sort of my backend C++ application, and I can just reach out to it and call the service on the browser. Or of course, the browser can call in to a service, and it doesn't need to know whether the service is in C++ or Node or Akka. It can call any service that sort of advertised within this network. And there's more stuff you can do. So you can plug in open tracing. You can plug in sort of a metrics backend like Prometheus. And suddenly, all the metrics just start to be recorded throughout the system without any changes required by the developer. Because the Proteus client is constantly like seeking to dump metrics to this metric service, but if it's not available, nothing will happen because there's no demand. No traffic will flow. Likewise with open tracing. So you can start to advertise these services that sort of solve these problems without the developer needing to worry about them. Okay, so let me show how to start this up. Okay, so I'm going to start a broker on my laptop. I'm also going to start Prometheus. All right, then back here, I'm just going to change one thing about this application. So back in the record service, whereas before you can see I was plugging in this TCP server transport and binding to a host with a certain port. And you can imagine that introduces, of course, the problem of how does the client know what port that is? How does the client load balance between all of the different services that might be offering this functionality? That's sort of left to a client exercise. But here, if I change the model, instead of binding to a port, I'm going to connect out as a client to this broker. And the broker will then be able to route to me over that same connection. So I no longer need to bind to any port. I'm just a client that's offering services to this network. So I'm just reading some properties from a configuration file. Within this file is going to be, for example, the service that I represent, which in this case is Reactive Demo Records. So as soon as I connect in to this broker, anybody is going to be able to call me and ask for this functionality. Cool, so that's connected into the broker. And now on the other side, exactly the same way. The client is going to connect into the broker. It's then, and notice the difference here. Instead of having to call out to a certain port, I'm just going to say, I want to talk to this group, Reactive Summit Demo Records. I have no knowledge about where that exists. It might be in a data center, it might be running in the cloud, it might be in my laptop. But what it exposes is the type that is returned is an RSocket, something that extends RSocket. And so none of the other code around this has to change. It's simply adding this functionality in using the RSocket protocol. So I'll run this guy. There, it's got the same results, right? It's got the same, I asked for the same thing, but this time it's actually gone through the broker. It doesn't have a URL for that one. Okay, cool. So that's request reply. So then what about this ranking service? So let me go ahead and run this one. So there's a few ways we could do this. This one is a programmatic ranking service. So it's literally just looking at a single property of the thing, get story count. So it's going to say, if you ask me which is the better of two superheroes, it's going to be the one who's appeared in more stories, right? So I can do this programmatically. And then back in my client, so let's say I don't want to talk to the record service anymore. Now I'd like to talk to this ranking service, and I'm just going to pass it in some data of my choosing. So I'm going to pass it in a couple items. It doesn't come from a database. I'm just defining these and see which one wins. So in this case, this has a story count of 20, so this should win. Cool. So it printed out the ID of the winner, which in this case was Stefan here. So we can do this programmatically. What we could also do is I'm going to kill this ranking service, the one that's written in Scala, and I'm going to run another one, which is written in JavaScript. And exists in a web browser. So what this is doing is sort of taking the same protobuf IDL, and instead of generating Java or Scala code, it's generating JavaScript, which then connects into the broker in exactly the same way. So as soon as I visit this web page, I've now become a server that's in this network of microservices. So my browser is functioning in exactly the same way as that Scala application was, but it's implemented a little bit differently. So now when I go ahead and call the same client application, notice I haven't changed any code here. It's still looking for exactly the same service as it did before. Now it's going to display it and give me the choice about which one is going to win. And see, and it's finished the request. So I chose 0, so it's not printing in the ID, because that's the default value. But I could do that again. And so this lack of a distinction between client and server really opens up the world of possibilities for microservices. So for example, I could find a chat application with no backend at all that's just completely implemented in people's web browsers. Or I could start to implement distributed caching where caches exist only in the user's phones or web browsers, and they can all call each other completely independent of where they are. So, okay, it's beyond this one. Let's just pull it all together with this tournament service. So this is another kind of cool use of reactive streams. We don't have to get into the code too much, but what this is doing essentially is making a database query and then sort of mapping over the values as they stream in from the database, comparing them against each other, and flat mapping to this comparator service, which for the moment is running on my browser. And then sort of iterating through that until every superhero has been pitted against every other one in the tournament, and there's finally a winner. But the cool thing about this is this, right? This is doing something extremely complicated, right? It's windowing, it's flat mapping, it's calling other services. Nowhere in here have I defined circuit breakers. Nowhere in here have I defined flow control. It just happens automatically via the implementation of these reactive streams operators. So if I say, give me 5 items, it's not going to ask for 100,000 items from the database and then throw away the rest. It's going to ask for 5 items. Okay, so I'll run this tournament service. And I'll take a moment to go into the UI of the Netlify broker. So in addition to just doing the routing, there's also things I can configure in here. So if I go in, I can see what brokers are available in this cluster. I can also see all the services that are connected in to the broker. So I can see the tournament service that just connected. I can see the tracing service that I set up at the beginning, right, and the metric service. And then there's sort of internal services that the broker itself offers, so you can query it via like a command line application. In addition, I can create sort of access keys, so I can have different access for different teams, right? So I can create this, and then these were just hard-coded in the example application, but I can create these and give access to different APIs to different teams within my company. And there's also a sort of monitoring system, so I can see in real time traffic that's flowing through the system and what services are connected in where. So at the moment, there's no traffic flowing because I'm not running anything, but I have all the services there. So I'm going to go ahead and run the client again, which now instead of calling the records service or the ranking service, is going to call into this tournament service. It's going to choose 256 items from the database and stream through them until it finds a winner. As I said, right now this is in my web browser, so I'll have to click really quickly. So you can see it's streaming one by one these items from the database, calling my browser as a service, and I'm deciding sort of who the ultimate winner is. And without back pressure, this would not work because my browser would suddenly get 100,000 items or whatever from the database, but it's not. It's waiting until I click to request the next item. Okay, so I don't need to actually finish this. What I'm going to do is close this, restart the programmatic one. So as you see here, the ranking service disappeared. As soon as this one comes up, it's going to reappear here. There it is. And then I'll start to run the client again. Actually, before that, I'm going to go make this bigger. Just so we can see some traffic start to flow. There we go. So then I can actually dig into any one of these and see exactly what nodes are there. So this is on the service level. That's already finished. So the winner was Iron Man, right, of the ones that I selected. And you can see it going through all 1,024 items and running 10 rounds of this tournament and pitting them together one by one by one. And it's all asynchronous, so the rounds are sort of intermingled. So as soon as somebody wins one round, it's going to start the next round. But eventually, it gets down to the winner. Okay, so if you remember back at the beginning, I started this Prometheus service. So look what's been happening back in the background. No code that I wrote to do this. It's just happening at the network layer because as the traffic passes through the broker, it understands what requests are going on and it understands that there's a recipient for the metrics information that it'd like to dump. And so all this just ended up in Prometheus. So I get a lot of detailed information because it's running a sort of a set of default, on the JVM, there's sort of a set of default metrics that it's collecting about memory and latency. And then for each of the individual services, I'm getting latency information. Then in addition, it's also capturing distributed trace information for each of these services that I ran. And so I can go back and sort of inspect any one of these traces. So you can see the few times that I ran it. So yeah, so I mean, RSocket really represents an easier way to build microservices. It lets you write business functionality and not deal with the details of your distributed system. It just lets you connect things together in the most obvious way and sort of use the system that you're building. And you can do this, as I pointed out, in any language. And then once you build it, you never have to change the code. You can go back and change the transport the next day. If, say, I switch to Azure and then suddenly I have, RDMA access, and I can start using RDMA as a transport. If I want to plug in Aeron and get an order of magnitude lower latency for that particular hop, I can plug in Aeron. But none of the client code ever needs to change because it's using this sort of the RSocket abstraction. It's a layer above the networking. And so that's why I think RSocket is pretty cool. Great. It looks like it's 12:10, so I'm out of time. Thanks for coming.